So, you're going to get sick of hearing me tell you about how awesome the periodic table is. The periodic table is just loaded with information. Already we've talked about how we can look at it, and chemical name comes from the symbol. The atomic number tells us the number of protons, the number of electrons. And what we're going to find out as we progress through this semester is where it is on the periodic table also has to suggest what its typical charge is going to be when it ionizes. Again, this is the typical charge, not the only charge. So where you are on the periodic table denotes whether you're going to be a positive charged species or a negatively charged species, ideally. So if we just take a look at the periodic table, we see this nice little dividing line. Right? This line shown here represents the break between the metals, which are over on the left-hand side of the periodic table. I guess this is your left. I don't know. I don't know. This side of the periodic table. These are the metals. And then we have the non-metals. Metals typically are all solids. They all kind of shiny. They have a certain luster. It's what we think of as a metal. You know, steel is a metal derived from iron. So this behavior, metals, when they ionize, typically will form cations, positively charged species. Metals will typically form positively charged species. Whereas the nonmetals, those over on the other side of the periodic table, typically form anions, or negatively charged species. A good example would be something like chlorine, whereas a good metal would be something like sodium, would form sodium cation. So this would be the sodium cation, or the chlorine anion. And these two compounds react together. If you bring the sodium ion, it'll be attracted to the negatively charged chlorine ion, and the two will form a new compound, NaCl, the name of which is sodium chloride. Notice the name actually isn't chlorine, sodium chlorine, it's sodium chloride. And so there's implied information within the name. And so what we're going to talk about today is how to name these species. So going back to the periodic table, we see behaviors associated with each of these. Now, your book has a nice little chart on page 54 for the 10th edition of your book, though you can find it almost anywhere, that lists common charges. You kind of just have to memorize these. As it turns out that everything in the first column here typically forms a +1 ion. The second one forms a +2 ion. Whereas everything over here, the last column typically doesn't form any ion. This row here, the halogens typically form a -1 species, whereas the chalcogens typically form a -2 species. Nitrogen and its family generated a -3 species. And again, this line represents a break. So how these materials, how the tin and indium and like behave is different than how the silicon and phosphorus and boron behave. All right, so take a look at the periodic table in your book and look at the commentaries. You have to start memorizing the typical charge forms. In general, the ones we can trust are +1, +2, -1, -2, -3, -4. Everything else has fluxional charges, except for aluminum, which is usually +3. All right. And these will be the charge that typically form in an ionic compound. Now, how can you tell if something's an ionic compound? That's a good question. How can you tell? Typically, ionic compounds are composed of at least one metal and one nonmetal. Not always. If you see a metal in a material that has more than one element, dollars to donuts, it's going to be an ionic compound. Most ionic compounds consist of at least a metal and maybe one or more nonmetals. So look for that combination, a metal and something else. You can almost bet it's going to be ionic. And if you're lucky, it's one of these nice friendly ones like sodium or magnesium that has a typical charge that it always defaults to when it's an ionic compound. What about the transition elements? What about those elements in the center part of the periodic table? Those elements have charges that vary, and we can't trust the charge. We have to explicitly say the charge, and I'll talk about those more in a few seconds. So when we deal with a metal and a nonmetal, when we deal with ionic compounds, we name, for the procedure for working with these ionic compounds is that we name the cation, and then we name the anion, and we bring the two together, and that makes the name. All right, so we name the cation. This is the sodium cation. The anion, so the cations are always named. How do we know this is the cation? Well, it's the metal. All right. The metals typically form the positive charge species, typically form the cations. So we know that this is a metal. Therefore, we can use that as a gauge for whether or not it's the cation or the anion. Also, traditionally, we have a tendency to write our structures, our formulas, cation, anion. All right. Positive charge one goes first, negatively charged one goes second, typically. So you could, even if you didn't know what it was, something like CrBr2, we could say that this would be the cation. Now, there are some ionic compounds that don't contain metals, and we'll talk about those near the end of this lecture. So, cation, anion. So, cation's easy. So, this is the sodium cation. Yay, nothing too hard. Now, when you deal with a transition element like iron, we have to sort of start to work with other behaviors. Iron can have a +2 charge or a +3 charge, typically. How do we know which? Well, we don't until we're told, or we have to figure it out from inferred information. So iron, in this case, would be an iron 2 cation, and we write that in brackets, where this denotes the charge. That's all it denotes. The 2 in brackets only talks about charge. Burn that into your brain because it'll come back over and over and over again. Now, naming the cations is easy. We just take the name and we add the word cation. No big deal. Now, the anions are a little more difficult because there are a wide range of anions. So for the anions, for the negatively charged species, depending on the nature, if it is the element in its typical ion, so if it is the element in its typical ionized form, like Cl-, this is derived from chlorine. Instead, we drop the INE ending and we add the IDE. So this becomes chloride, or the chloride ion. So if we have something like NaCl, name the cation, sodium, surprise, with chlorine, the ion in its typical charged state, this is chloride. What about something a little more complex? CA8, Br2. Again, this is the calcium ion. It's implied that this is really Ca plus 2, and contained within that are a bunch of bromines, each of which has a -1. But there's 2 of them to balance out the charge. Sorry. The calcium has a +2 charge. It needs to balance out that charge with 2 bromines, Br-. This is the typical charge for a bromine. We can look it up on the periodic table and see that it typically forms a -1. The name for this compound is calcium bromide. Simple. Name the cation, name the anion. Done. Now, what about something like FeBr3? Well, in this case, the charge on the iron isn't explicitly told to us. But we have 3 bromines, each with a -1 charge. That would imply that the iron, if this is all a -3 charge together, 3 bromines each with a -1, total of -3 charge, and there's only 1 iron, it has to balance out that charge. So to balance that out, it would have to have a +3 charge. So that iron is a +3 compound. And so the name for this iron 3 bromide. Now don't get lulled into saying, oh, it's iron 3 because there's 3 bromines. That's not exactly true. It's iron 3 because it's a +3 charge. What do I mean by that? Well, let's take a look at 2 of my favorites, FeO, P2O3. We can look at the periodic table. Here's the secret. You always know at least one of them. You're not going to be given something that you can't infer what the charge is, either from where it is on the localized periodic table or some other information in the problem. Oxygen typically has a -2 charge. Again, we can get that from where it's located on the periodic table. And for those of you that aren't familiar, this is either memorization or something we'll talk about a little bit later called the Octet Rule. Iron, because this is a -2 charge, that iron has to be balanced out with a +2 charge. All the positive charges have to cancel out all the negative charge for it to be balanced. So the name of this compound is iron 2, and then oxygen in its typical typical charge, oxide. Oxygen is a little bit weird. It drops the ending and becomes IDE. This would be iron 2 oxide. Iron 2 oxide has 1 iron. Very annoying. We can do a similar analysis for this compound. We see that there are 3 oxygens, each with a -2 charge. And the iron has 2 of them. And the 2 of them together have to cancel out plus -6. So that means that all of these together would have to be +6, or each would be +3. Right. So this compound would be iron 3 oxide. So that's naming of simple binary halides. Now you should also be able to go backwards from the name. So if you talk about copper 1 oxide or rubidium nitride, you should be able to generate the formula from that name. And a lot of students find this much easier, right, because you're told all of the information explicitly. All right, so copper 1 is a Cu+, +1 is implied, where oxide is O-2, and so that would require a second copper to balance it out, copper 2 oxide. Rubidium nitride, symbol Rb, +1 charge, +1 charge. Nitride, nitrogen in its typical state, -3, based on its location on the periodic table. So it would require 3 rubidiums to balance out the charge on the nitrogen. There. So that's simple binary ionic compounds. Notice, only 2 different elements. Name the cation, name the anion. Now, this is where it gets interesting. What about 2 SO4 K ClO4? How do we go about naming these beasts? Well, it turns out that if you see more than 2 elements, what it means is that these are not simple ionic compounds. They often contain more complex structures, ions that consist of multiple atoms, what we call polyatomic ions. Polyatomic ions aren't any different than regular ions, except they are groups of atoms. They're small molecules held together that also happen to have a charge. Most of the ones we deal with are the oxyanions. And for the oxoanions, you should start memorizing the 8 anions. These are the ones that I call the 8 anions. The reason for this is all of the families of oxoanions, the naming sort of stems from the base 8 ion, the more standard, most common. They're also the most common ones. So, how to memorize this? There's 8 of them. There's 8 of them, and that's why I call them the 8 anions. All right? The 8 common polyatomic ions. These ones all have the ending ATE. All right? And how do we know them? The thing is, we have to memorize both their charge and the number of oxygens. It's not quite straightforward. The trick is to start by writing out this upper right-hand corner. If you want to start memorizing things, writing out the upper right-hand corner. So if we go carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine. I like to also include selenium, bromine, and then iodine. So this is just the upper right-hand corner of your periodic table. Just grab your periodic table and write that out. Right? We're just going to ignore the oxygen and the fluorine. Why? Because they don't form polyatomic ions, like the nitrate, sulfates, and the like. Each of these compounds has a certain number of oxygens and a specific charge. CO3 minus 2, NO3 minus 1. I'm just going to put the minus 1 in there, even though we just leave out the 1. It's just helpful for seeing how the numbers go. PO4 minus 3, SO4 minus 2, ClO3 minus 1, SCO4 minus 2, ClO3 minus 1, PO3 minus 1. These are the common polyatomic ions that we're going to encounter. This is, they all end in the ATE ending, so this is carbonate. This one is nitrate. Phosphate, based off phosphorus. Sulfate, based off sulfur. Selenate, based off selenium. Chlorate, bromate, and iodate. Flashcards are probably the easiest way to do this. Or, you know, you take a corner of your notebook, and every time you turn a page, you write carbon, nitrogen, oxygen, fluorine, phosphorus, blah, blah, blah. There's a couple trends. There's no rhyme or reason. Generally, the number of oxygens decreases going across the periodic table. The number of charge decreases, but there's no rule. It's like you can just memorize. Your best bet is to just nail one or two of them and then build the rest from memory. So these are the common oxoanions. They're very prevalent in nature, particularly carbonate, nitrate, phosphate, and sulfate. Huge players in biological systems. Less so for chlorides and bromates and iodates. Now, if it were just these, we'd be lucky. We could just say, oh, look, this material contains the SO4 ion. If you see the SO4 present, you can bet that it's a sulfate, and it has an implied -2 charge. And so there's an implied -2 charge in there, which makes sense because there's 2 sodiums, each with a +1 charge, and so that would cancel out. Good. But if you have the I, you'll notice that this is a ClO4. Well, none of these are ClO4s. It's close to this chlorate, but it's not a chlorate. It turns out that the polyatomic ions, there's a whole family of oxoanions. And these oxoanions all vary with the number of oxygens. We can see that this compound is named sodium sulfate. Notice, nowhere in the name does it say how many sodiums. The number of sodiums is implied from your knowledge of what a sulfate is. So if you were to deal with potassium phosphate, you would have to know that phosphate is a PO4 -3 ion, and potassium has the symbol K, has a +1 charge, and so potassium phosphate would be K3PO4. 3 potassiums to balance out the -3 charge of the phosphate, K3O4. We name these other oxoanions. Well, it turns out that all of the oxoanion families are very similar. So let's take a look at the chlorate and use that as our starting point. ClO3 minus. So one of the simpler derivatives of the chlorate ion is one that contains one less oxygen. So if we reduce by one less oxygen, ClO3 becomes ClO2, and the charge stays the same. And this within the family of oxoanions that we look at, the charges all stay the same. Once a small blessing. Right? So these materials with one less oxygen get the ite prefix. Sorry, the ite ending. These ions with one less oxygen get the ITE ending. So this would be chlorite. So this is the chlorite ion. So something like the nitrite ion, which you might have heard about as being implicated in certain types of cancers, the nitrite ion would have one less oxygen than the nitrate ion. So if we know what nitrate is, NO3 minus, we can go, oh, this is NO2 minus. That's the nitrite ion. And NO2 would be sodium nitrite. Well, we know that this is an iron 3. We know that sulfite is a derivative of sulfate. Sulfate is SO4 minus 2. Well, sulfite would be SO3 minus 2. And so this compound would be Fe2S3. Prove that to yourself. Now, if only life were so simple, it turns out there are two other derivatives. If you increase the number of oxygen, you can generate new anions, ClO4. These get adorned with the per prefix, and they keep the 8 ending. So this would be per chlorate. This is the perchlorate ion. Okay, ClO4, potassium, perchlorate. And lastly, you can decrease it by another oxygen. ClO2 becomes a ClO minus. So we've depleted by a total of 2 oxygens compared to the chlorate. This gets the hypo prefix, and it keeps the ITE ending. So this would be hypo chlorite. Turns out hypochlorite, the hypochlorite ion is the active component in bleach. So, one ion gives you 3 others. These are all within the same chemical, all within the same family. Different number of oxygens, different number of charges. That's why I highly recommend that we spend our effort memorizing the ATE ending materials and generating those other ions procedurally from those. Now, it turns out that there's one other feature. You can take any anion or any salt, and if you replace it, the sodium, the cation, if you were to instead substitute a proton, H+, or the hydrogen ion, you generate acids. We'll talk about acids and bases in greater detail later in the semester. But they all have their own unique names. So we can do something similar with the sodium. We can conceptually replace it with an H+ to generate H2SO4. The names of these materials, the acids, have names based upon the anions. So we focus on the anions. The type of anion that it has alters the name of the acid. The simplest acid, those generated from the element in their gas phase, in their aqueous systems, that's when they're dissolved in water. We don't call these things like hydrogen chloride or anything like that. That's not how we discuss them. These are acids in solution. This one, they get the hydro prefix, an IC ending, ic, hydroic acids. So this would be hydrochloric. That's only for the elements in their typical anionic form. For the polyoxo materials, the polyoxo anions, for the oxo anions, the naming is very similar. Anything that ends in ATE becomes an ic prefix, an ic ending as well. So this is the sulfate ion. This would be sulfuric acid, hydrochloric acid. It's as simple as that. Anything that ends in ate becomes ic. Anything that ended in ite becomes OUS. So HNO2, which is derived from the nitrite ion, this would become nitrous acid. All right, a lot to keep track of. Again, note cards. Make yourself a note card, put the name on one side, write yourself a big old NaCl on one side, and on the other side, you write the name, sodium chloride. Tons of examples in the book. Right. We're going to be beating this really hard. This is a huge component of this early part of class. Correct nomenclature. Now we're only talking about the ionic compounds here. We're not dealing with any of the non-metal based materials, but this is enough. All right. Memorize those 8 anions and then be able to generate the names for the other species. Be able to take the name and convert it back into the formula, and then take the formula and convert it back into the name. We'll have tons of examples in the homework.